Okay, right. A very good evening to all present for this third and last set of lectures in the series Celebration of 100 Years of Quantum Physics, organized by IAPT RC15. We are aware that UNESCO has declared 2025 as the year of quantum science and technology. This year, we celebrate 100 years of beginning of the use of quantum mechanics in interpreting physical phenomena and defining the relation between particles and photons. The first session of our series was on 18th May, when we listened to Professor Ajoy Ghotok speaking on Schrodinger equation and uncertainty principle. This was followed by Dr. Bhupati Chakraborty speaking on pathways in the center state, significance of work of Essenbosch in old quantum theory. These two lectures were a great beginning of our series of lectures. In the second, can you please silence the mics? In the second session of the series on 2025, we listened to Professor G.P. Dash speaking on from quantum mechanics to quantum materials, followed by Professor P.K. Aluwalia speaking on a quantum material from the flat land of crystals, graphene. Two erudite presentations illuminating the areas of interest. Today, we have gathered for the third and last session of the series. We will have two lectures. The first one will be delivered by Professor Bhupendra Dev, professor at the Center of Quantum Engineering, Research and Education, TCG Centers for Research and Education in Science and Technology, Kolkata. He will speak on quantum mechanics to quantum computers, quantum science to quantum technology. The second lecture will be delivered by Professor Ananda Dasgupta of Department of Physics, Indian Institute of Science, Engineering and Research, Kolkata. He is also the Vice President of IAPT RC15. Professor Dasgupta will speak on coherent and squeezed states, theory and applications. Once again, a hearty welcome to our lecturers of the day and to all the participants. Before I invite Professor Dev, I would like to give a short introduction about him. He's a very well-known scientist, but still, I think that will be a good idea to just remember his special achievements, at least a few of them, not all of them, but a few of them. So Professor Dev, at the moment, is a professor at the Center of Quantum Engineering, Research and Education at the TCG Center for Research and Education in Science and Technology, Kolkata. His PhD degree he had from State University of New York at Albany, and then he worked in Europe and at different places before he joined IOP Bhubaneswar, from where he moved to Indian Association for the Cultivation of Science, Kolkata. Since 2017, when he superannuated, till 2020, he was a visiting professor at Indian Institute of Kharagpur, working there as well as in the School of Nanoscience and Technology. In 1921, he took up a challenge of building a superconducting quantum computer at CG Crest and started working on it. He has set up a 1-qubit superconducting quantum computer and is working to expand it to a 5-qubit quantum computer. Professor Dev discovered superconductivity in cobalt in 2020. He is currently researching on superconductivity of cobalt as well as cobalt disilicide, a material with good potential for superconducting quantum computing technology. He has worked extensively at the Institute of Physics as well as in ISCS using molecular beam epitaxy and scanning tunnel microscopy and photoemission electron microscopy. He has received several honors. I will mention only a few. Starting with from his alma mater at State University of New York at Albany. Later on, he got DAE Rajaramana Prize in Physics of JNCASR. He is an elected fellow of Indian Academy of Sciences, National Academy of Sciences, India, and West Bengal Academy of Science and Technology. A very distinguished scientist. We are very happy to have you here, Professor Dev, with us here to deliver the lecture. Please go ahead. Thank you.
Oh, I'd like to thank you for your very kind introduction, but I would like to thank Professor Ahluwalia and the IAPT Regional Council 15 for the invitation. And it's a great honor to be here speaking. So my topic is quantum mechanics to quantum computers, quantum science to quantum technology. As quantum mechanics represents the quantum science and the quantum computers represent quantum technology. As we know that the basic science came first, and then whatever knowledge we gather from basic science, that has been applied to develop technologies. Think of electricity, static electricity and current. After the discovery, someone just thought that we can make a heater, but Thomas Alva Edison made the light bulb. So these are the technologies that came from the basic science knowledge. Similarly, whatever knowledge we gathered from quantum mechanics or quantum science has been applied to develop quantum technology. So this is okay. So this is my outline of my talk. I'll give a brief history of quantum mechanics. You must have heard it already several times, but just for the completeness of my presentation, I'll still briefly mention it because I want to show where the transition took place from quantum mechanics to quantum technology. So then I'll discuss the first quantum revolution, which did not harness all the properties of all the knowledge of quantum mechanics, and harnessing the full power of quantum mechanics and the second quantum revolution, and quantum computers comes in the second quantum revolution. And then a glimpse of the development of a quantum computer in our laboratory would be followed by conclusion. 1900, okay, some part was getting blocked. In 1901, that's the first year of the 20th century, Max Planck explained the black-body radiation by introducing a formalism that introduced a mathematical trick and some constant, which was later named Planck's constant H. But in 1905, for explaining photoelectric effect, Einstein gave a meaning to that mathematical trick. That means what H really means, but the Planck's constant. Then 1913, Bohr gave the model of atoms, and which that is successfully reproduced the absorption spectrum of hydrogen, which was not adequate for other complex atoms. 1922, atoms of quantum spin that was discovered. The Stern-Gerlach experiment was done with silver atoms, and it showed that it has two discrete states of spin in that. And from 1922 to 1929, in these 7 years, there had been tremendous developments of quantum ideas within a very short span. So this is what I'll just mention, that 1923, Arthur Compton actually showed that even high energy photons can transfer some momentum to charged particles. That means the light photons can behave like particles. Then came Pauli exclusion principle, which says that all 4 quantum numbers of electrons cannot be same for 2 electrons. And this Pauli exclusion principle explained how Bohr's model of atom can be connected to the structure of the periodic table and was later extended to all fermions. Then 1925, the matrix formulation of quantum theory came in. And this was after his famous trip to Helgoland, Werner Heisenberg derived the quantized energy levels of one-dimensional oscillators in terms of physical quantities, such as transition probabilities, that could in principle be measured. 3 fundamental papers by Heisenberg, Max Born, and Pascal Jordan developed the first consistent formulation of quantum mechanics based on matrices. So where is this Helgoland? It's very close to my home. I can say, I'll explain what it means. This is Helgoland. It's a very small island in North Sea, in the northern part of Germany. It belongs to Germany. So I lived in Hamburg here and worked here in Daisy. So every summer I used to make a trip to the coast here of the North Sea. And this is the Elbe River going from here. And at the mouth of the Elbe River, this is at Cuxhaven. This is a harbor. And from here, by boat, one can go to Helgoland. This is about 60 kilometers. And later on, I spent a sabbatical year also again in Hamburg in Daisy. At that time, I lived in Pinneberg, another smaller town here. And Helgoland actually belonged to the district of Pinneberg. So it was, Helgoland was in my district. So quantum mechanics was developed there. And this is the island that you see there. It's actually two islands. And this is the main island. That's very small. 1 square kilometer is the area. That means it's just 200 acres. Population is about 1,000. So quantum mechanics was developed on this small island there by Werner Heisenberg. So 1925 also saw the wave-like behavior of matter. That's the de Broglie, showed that any moving particle has an associated wave. This was the hypothesis of de Broglie. And this actually cemented the concept of wave-particle duality in quantum mechanics. 1925, electron spin was discovered by Uhlenbeck and Gaudsmit. And then 1926, Schrödinger introduced his famous equation, Schrödinger equation. So Erwin Schrödinger derived the wave equation that is central to the modern quantum mechanics. It was soon proven that this formalism was equivalent to Heisenberg's matrix mechanics formalism. But physicists were already familiar with wave mechanics that allowed Schrödinger's approach to rapidly gain popularity. 1927, it showed electrons behave like waves. Earlier, Compton showed that light behaves like particles. Now, through electron diffraction, it was shown that electrons behave like waves. It's a Davison-Garmer experiment. You all know about that. It's experimental confirmation of his prediction, like de Broglie, showing that electrons scatter from a crystal in the same way as X-rays do. We all know that X-rays are waves. Since the electrons also scatter like X-rays, so electrons behave like waves. Did I miss something? Okay, yeah. So understanding wave function. This is actually when Schrödinger worked out his equation and solved the wave for the wave function. He didn't really know what it means. It was later in 1927, Max Born gave an explanation to that. The Max Planck provided a probabilistic interpretation of Schrödinger's wave function, stating that the squared amplitude of the wave function gives the probability that a particle will be observed in a particular position or that a measurement will yield a particular result. So in that, the Born's rule became a postulate of quantum mechanics. Then in 1928, Dirac developed a relativistic equation for electron, and that also provided for the anti-electron or the positron, was the possibility of that. 1929, Heisenberg's uncertainty principle was generalized. It was not just delta x, delta p is less than or equal to h cross over 2. It showed that for other non-commuting operators also show the same behavior. We know that delta E times delta T also follows the uncertainty relation. Then in 1929, it's a very important things came up. Quantum description of solids. Felix Bloch provided a theorem that allowed the description of the behavior of electrons in a periodic structure of crystalline solids. And his theory offered the basis for the concept of electronic band structures. So this quantum application of quantum theory to solids that actually had sown the seeds of quantum technology. So that is the first quantum revolution. That's what I'm going to talk about now. So quantum mechanics provided an understanding of the properties of solids like silicon and germanium. These are semiconductors. And then transistor was invented in 1947 in Bell Laboratories using germanium. They made a transistor with germanium. And now we know that what important invention it was that actually set out the first quantum revolution with revolutionary technology. So this is the birth of first quantum revolution. And this curve shows actually, it's called the Moore's law, the number of transistors per microprocessor. So 1947, there was only one transistor, size was about a square centimeter. But then the processors have been developed with a size of 1 inch by 1 inch and fitting more and more transistor because transistor size was become smaller and smaller. Around 1970, there was already about 2,000 transistors on a chip, but the number of chips on transistors on the chip actually was growing exponentially. Every 2 years, the number was becoming double. So it has become around 2021, it's about 40 billion transistors on the microprocessor chip. This rapid exponential growth has developed our supercomputers that are available today. So after this invention of transistor, how things moved in terms of development of classical computers, it actually, the genesis of this is a predecessor of transistor was a vacuum tube. And using vacuum tube, the first computer was made, is called ENIAC. About 17,000 vacuum tubes were used there, but very little computing power of that. And after the invention of transistor, it rapidly grew. And you see that even in 2017, about 20 billion transistor per processor. And today's supercomputers, this one is Frontier in Oak Ridge National Laboratory in the USA. That contains about 10 to the power 11 transistor, right? And this then operates at a very high speed, at 1.2 exaflops per second. Exa means 10 to the power 18. So 1.2 times 10 to the power 18 operations per second. Now you know that the mobile you are holding in your hand, they also have like iPhone 14 Pro contains about 16 billion transistors. And they are, you know, their capability now. Now that set out the first quantum revolution, and which is now about 7 decades old. The second quantum revolution is about 3 decades old. So I'll go to the second quantum revolution later. But first, I'll give a few more examples of the first quantum revolution, which other technologies it has provided. I'll give some examples only. So invention of atomic clocks in 1950s, invention of ledger 1960, and the superconductivity discovery in 1911, but its quantum understanding came in 1957 with the BCS theory, Bardeen, Cooper, and Schrieffer theory. So what sort of technology they provided? What you see here, where you are holding your mobile in your hand and you're looking for the Google map to see something. So this is, of course, a quantum technology, but utilizes another quantum technology, which are clocks, atomic clocks. The GPS system is a 24 satellite orbiting around the Earth. And say, for example, on the Earth, you are sitting at this point, this red point, holding your mobile. And this is also rotating. So now the satellites are also rotating. So important thing is that the satellite can directly see your mobile. They can determine the distance using the atomic clock in there. So at least 3 or 4 satellites have to see your mobile, then it can tell your location precisely. And that's how it works. So this technology also came from the cesium atomic clock, a quantum technology that came from the first quantum revolution. Then superconductors, what is that? If you have a superconducting material below a certain temperature, so called transition temperature, TC, it becomes superconducting. That means it has no resistance. If you can set out a current through that, it can remain there almost forever. Say you have a loop, a ring of superconducting material, and you are holding a magnet here. If you suddenly take the magnet out, the change of magnetic flux will set in a current through this loop. And this current can flow for even 100,000 years because there is no energy loss. I square R is the power loss and R is 0. So there is no loss. Now, if you make a coil out of superconducting materials, you can pass a very high current without any loss, energy loss. And that can set out a very strong magnetic field, which has many technological applications. The solenoid. Here you see the magnetic resonance imaging. And inside this, you have a very strong magnet. And this magnet is actually done using superconducting coil. Without superconducting coil, you wouldn't have this high magnetic field that is required for more precise imaging. Then superconductors also repel magnets. So you know that if you put a magnet on a piece of material which is superconducting below a certain temperature, say high TC superconductors, at room temperature, they are not superconducting. So the magnet will sit on that. But now if you pour liquid nitrogen on this, it undergoes superconducting transition, becomes a superconductor, and then it will repel this magnetic field. This principle was used to make trains which can actually fly. It's a maglev train, magnetic levitation. That means it doesn't contact with the track, so it makes a gap and it practically flies. So it's a very high speed. So these are some of the technologies that came from the first quantum revolution. Also, I'll give some other examples, which are also very important. Let me ask you a question. If you have a copper wire and you connect a battery and a current meter with that, you know that current will flow through it, will measure the current. But if there is a break in the copper wire, would you get a current flow? I think your natural answer would be no, but that is the right answer. But yes is also a right answer. Because if the gap is very thin, a few nanometer, then electrons can actually tunnel through that gap. This by a phenomenon called quantum tunneling. And you must have studied in your quantum mechanics course that if you have a potential barrier and you have electrons on this side, it can tunnel through this barrier and it can emerge on the other side. So you can get a current through this. And this principle has been used to make the strongest, the most high resolution microscope called the scanning tunneling microscope, which has an atomic resolution. With that, you can see even every atom. So this is a picture from our laboratory in Institute of Physics, Bhubaneswar, of a silicon surface. So each spot is actually, this bright spot is a silicon atom. This we published in 2003, more than 2 decades back. And you can see even the surface of the unit cell. This is the unit cell. And with that, you can repeat the whole surface. So that means you can actually see atoms with this scanning tunneling microscope. But what is more interesting, you can also hold an atom, drag it from one place to another, and drop it there. Like with your finger, you are holding a marble from one place and taking it away, placing it somewhere else. You can do the same thing. Your finger is like a tip, this scanning tunneling tip, and this is like this atom is the marble. What you see here is written, you can read, is written IBM. And each of these dots is actually an atom. Color is a false color. So this is written with a 35 xenon atoms on a nickel surface. You can count the number of dots, then there are 35. These are 35 xenon atoms. So what you are doing here is it's a quantum pen to write with atom ink. Here ink is atoms, and the pen is works through the quantum tunneling process. Of course, this was written in IBM. Another technology that came from the first quantum revolution is the ITER, this International Thermonuclear Experimental Reactor, that causes nuclear fusion inside that to produce energy, this artificial sun. It uses superconductivity as well as quantum tunneling. superconducting magnets actually hold the plasma here inside. And plasma means say proton-proton, what happens in the sun. Proton-proton fuse, and this fusion releases energy, and that's how the sun gets the energy. Without fusion and the quantum mechanics, there would be no light or no heat from the sun. Sun would be a mass without any energy. Now, what quantum principles was not harnessed in the first quantum revolution? I'll talk about that. And that brought about the second quantum revolution. So the second quantum revolution is based on two other quantum phenomena. These are apparently very strange phenomena, and it's very difficult to understand, but I'll explain it. But if you feel that it's very difficult to conceive, you are not the only one. Even the most famous scientist of 20th century had difficulty in understanding that. That is Einstein. Anyway, so the second quantum revolution has utilized these quantum phenomena, and it has provided quantum technologies like quantum computers, quantum communication, quantum cryptography, quantum sensors, all these things. But of course, I'll not have time to talk about all these things. I'll just pick up quantum computers, the principles behind it and how it works. So what is a quantum computer? A quantum computer is a computing device that leverages the principles of quantum mechanics, such as superposition and entanglement, to perform calculations. Unlike classical computers that store information as bits, that means 0 or 1, which is basically turning off or on a transistor. Quantum computers use quantum bits or qubits, not just classical bits. It's quantum bits, it's also called qubits, which can exist in multiple quantum states simultaneously. You know, the classical bits can stay either at 0 or 1, but quantum bits can stay in multiple quantum states simultaneously. That is the superposition principle is applied there, allowing them to solve certain types of problems much faster, often beyond the capabilities of classical computers. Now you see the modern classical supercomputers have about 10 to the power 11 bits, that means 10 to the power 11 transistors in that. However, current quantum computers have only about 100 qubits. So it's a very tiny, it's a baby basically, compared to the classical computers. Even then, it has already displayed powers exceeding that of these classical supercomputers. I'll just give you two examples here. It's in 2019, Google performed a calculation with their superconducting quantum computer in 200 seconds. And they estimated that the same calculation would take even the best classical computer about 10,000 years to complete. And how big was this computer? It was only 53 superconducting qubits, as opposed to 10 to the power 11 bits in a supercomputer, classical supercomputer. And within 5 years, last year, they have made another quantum chip with superconducting quantum chip with 105 qubits, just about double of this. And they performed a standard benchmark computation in under 5 minutes. And that would take one of the today's fastest supercomputers 10 septillion years. What is 10 septillion years? That is 10 to the power 25 years. Can you imagine? It's much old, it exceeds vastly the age of the universe. So that means there's something that is impossible for the strongest superconducting, supercomputers available today. So that just gives a glimpse of the possibilities with quantum computers. Now let me explain the principles of superposition and entanglement. Superposition means it's the same particle can stay at two places simultaneously, or in two quantum states simultaneously. So it's the same electron. Classically, it's not possible. So this was when this was quantum concepts of quantum superposition and entanglement was explained even by Schrödinger in 1935. Within 5 years, in 1940, in the magazine New Yorker, this cartoon came up. So the two persons are skiing, Suddenly this man sees that this person existed at two places at one time, sometime. So if you are not watching, such things can happen in quantum world. So classically, one particle can be either here or here, 0 state or 1 state, or the position-wise, 0 position or 1 position. But in quantum, if it is quantum, the particle, then it can stay at two places simultaneously. Same electron can be here as well as here. So for the superposition, what really happens? The electron is in superposition until it is measured. If you measure it, then it collapses into one of the states. It doesn't remain in the superposition condition. So what happens when you insist that you want to measure and find out in which box, 0 or 1, the electron is? And measurement is actually an interaction of the quantum system with the measurement device. So that means you have already measured. So the superposition state doesn't sustain anymore. It collapses into one of the states, 0 or 1. But interestingly, you cannot tell which one. There is no definite answer. The process is intrinsically random. And this is strange, but it is real. So this random process you already encounter when you toss a coin. You can calculate the probability that a head will be on the top is 50% half, and the probability a tail will be at the top is half. But when you toss a coin, it comes either with tail or with head, and you cannot predict what will be the outcome. But how do you interpret that? This is statistical, so you have to carry out a large number of experiments. So if you carry out the same coin tossing, but 1,000 times, roughly 500 times it will be head, 500 times it will be tail. So that has a meaning now. So in quantum measurements also, if you want to derive a sensible answer, you have to carry out the same experiment, repeat the same experiment, maybe millions of times. Only then you can get the answer and realistic results. So superposition, Einstein had a problem with that. So he asked her, do you really believe the moon exists only when you look at it? Looking at it means it's a measurement. So if you don't measure, so quantum mechanically, moon exists in both states. It is there and it is not there. So Einstein just asked this question because he didn't accept this idea. So he says that God does not play dice. Like when you play with dice, you cannot predict which phase it will land. It's probabilistic. Einstein believed that everything should be deterministic in nature. So there is always intellectual duel between Albert Einstein and Niels Bohr. Niels Bohr represents the Copenhagen interpretation of quantum mechanics. Einstein says that God does not play dice with the universe. And Niels Bohr says, Einstein, stop telling God what to do. That means what God is doing, that is the reality. That means whatever quantum mechanics says, that is the reality. That's the claim of the Copenhagen interpretation of Niels Bohr. So let us go a little bit over to the mathematics. How do you represent a superposition mathematically? Think of an atom, say hydrogen atom. It has these different states. You know that ground state, first triad state, next triad state. Now, if you somehow restrict our system to the lowest two energy levels or the lowest two states, and just ignore the other ones, you can do it in different experiments differently. Then I can say the quantum state of the electron in this atom is represented by alpha times 0, this state, plus beta times 1. Alpha and beta are called the probability amplitudes, and alpha square is the probability of occupation of 0, beta square is the probability of occupation of 1, and naturally the normalized total probability should be 1. So this is electron is at the same time at both the states, 0, this state and 1 state. That's the superposition. Now, what is entanglement? Say we have two quantum particles. There cannot be entanglement with just one quantum particle. At least you need two. And again, there can be many more. So in this case, say the first electron is at 0 state, second electron is also 0 state. This can be a 1 state, but first electron in 1 state, second electron is also in 1 state. So this is the superposition of this and this. But superposition and then plus a correlation that represents the entanglement. I'll give you some cartoon to explain what these correlations are and how they can be different, these correlations. Look at this eagle flying. Now, if I say that this eagle, at this end, there's one quantum particle, another end is another quantum particle, and this quantum particle can be at 0 state or 1 state, down or up. This also can be down or up. So I can say that this can be 0, 0 or 1, 1. This is superposition of this, but this is a special correlation. That means when the left one is at 0, right one cannot be at 1. The eagle cannot fly like that, one wing down, one wing up. So this is a special kind of correlation. And mathematically, this has this representation. The state is 0, 0, and first quantum state particle is in 0, second one is also 0. The first one is 1, second one is 1, superposition of these two, and divided by 1 over square 2, that means probability is half and half. It's equal probability of occupation of these two. This is called an entangled Bell state. I'll not go into the details of this, what Bell states are, what Bell inequalities are. So those are more details. I'll not go into that. But this correlation can be also different. Like, for example, this seesaw. Here, if this is down, this has to be up because the swing cannot operate any other way. So this is 0 and this is 1. So it can be 0 or 1. Or this can be at 1, this is going to be 0. So this can be in a superposition between those two states. And again, this is another entangled Bell state, which is written like this. So this superposition and entanglement that gives the quantum computer the power. So Einstein quarreled with this superposition, and he also didn't like this entanglement. He objected to the idea of entanglement, calling it spooky action at a distance. Because this entanglement works, actually, it doesn't matter how far away they are. Say on the swing, if one end is at this place, other end is at the other end of the universe, also the entanglement can exist. Or I can also give some other examples, like, for example, a lady has two twin boys, and you know the characteristics of twins are usually, they have the same sort of characteristic. So now one of the boys is living with the lady at home, the other one has gone to America to study. Now, if the mother sees that the boy who is living with her has fever, she immediately feels that the other boy who is in America also has fever. So this is even they are at a very far distance. Just knowing the state of one, you immediately know the state of the other. You don't have to see it. You don't have to measure it. Schrödinger himself gave an interpretation of this clarification for superposition and entanglement. He says that you have a box. It's divided into two halves, upper half and lower half. Upper half has one system. This is an atom, which is a radioactive atom, which can decay. So this is like a quantum. It can either decay or has not decayed. So it's a superposition of these two states. Think this cat is another quantum state. It is either alive or dead, but that's so. If it is quantum, then it is both at the same time, alive and dead. So now they are also entangled in this case. This is not the superposition. Each is in superposition, but entanglement is that if this atom has decayed, I have a device here, the decay is detected, and then this entrapment, it releases this hammer. It actually is a glass flask with poison in it. So it breaks, and when this poison comes to the bottom chamber, the cat would be dead. If this has not decayed, nothing of this would happen, and the cat would be alive. So that means these two are entangled, the cat and the radioactive atom. If you know the state of one of them, you don't have to see the state of the other. You automatically know. If the atom has not decayed, cat is alive. If the atom has decayed, the cat is dead. This is called Schrödinger's cat. But all these things, even Einstein put forward some thought experiment called EPR paradox, Einstein-Podolsky-Rosen paradox. So Einstein was a very influential scientist. The scientific world was divided 50-50. So 50% believed in Einstein's postulates and 50% in Copenhagen interpretation, Bohr's postulates. But eventually, experiment has demonstrated that really entanglement and superposition happen. And these three gentlemen, Alain Aspect, John Clusar, and Anton Zeilinger, got Nobel Prize in Physics in 2022 because they have demonstrated entangled photons, and they have actually shown long-distance communication using these entanglement properties. So quantum mechanics was solidly established, all these two principles. They actually demonstrated communication, that means send a quantum state over a distance of 143 kilometers through these two islands. This is a set of islands near Morocco. And this is called the La Palma and Tenerife, about 143 kilometers away. And using entangled photons, they have communicated one quantum state. They sent a quantum state from there to there. Today, for quantum communication, that is used. Now, let me explain a little more about that classical versus quantum. It's this or this. If it is head or tail, 0 or 1, transistor on or off, this can be only one of them at a time. But quantum means both of them simultaneous, that is superposition. But if I want to give another representation of that, think of this like a billiard ball with the number on it. Now, if I say that the number is pointing up, I say this is 0. If the number is pointing down, it is 1. But this number can point in an infinite directions. So all these directions are actually superposition between the up and down. Right? So if I have a quantum bit or the quantum system, it's a superposition of 0 and 1. And so if I have another quantum system, that is also superposition, and there can be entanglement between them. So I need minimum 2 qubits for entanglement. Now let's see what is the basics of a computer. Think about classical computer, a transistor, turning it on or off gives a 0 or 1 state. So if I have a 3-bit register, that means 3 transistors. So I can have this for 3 possibilities, 0 or 1, 0 or 1, 0 or 1. So that means I can have all 3 0 up to all 3 1, and in between these possibilities, 8 possibilities. So I can represent the numbers from 0 to 7 using this classical register, but it can store only one of these numbers at a time, not all. But if I have a quantum register, then these are quantum bits, these are 0 and 1 simultaneously. So that means with 3 quantum bits, I can represent all the states at the same time. That means I can store all the 8 digits at the same time. The power counts is 2 states and 3 registers, 2 to the power 3 equal to 8. 8 numbers I can store at the same time. If I use 4 registers, then 2 to the power 4. 16 numbers I can store at the same time. So it grows up exponentially. This is the storage capacity. But if I talk about the operations, that also speeds up exponentially. Think about this maze like Alice in Wonderland. Now, if you put a ladybug inside here, and the ladybug is trying to explore, it wants to get out of this maze to find some food here. So it has to try, for example, this first try somewhere here is blocked. It doesn't find it. That means it has to try many times to find its path. But if you have a colony of ants and all of them go out and they try simultaneously all their different paths, they will find this exit very fast. So since, as I said, the storage capacity is also, they can store simultaneously a large number of digits or numbers at the same time. Similarly, they can carry out calculations in parallel, many of them at the same time. That gives them the speed. So the power of increases exponentially in proportion to the number of qubits, as you see here. And for bits, that means in transistor, for classical computers, power increases in 1:1 relationship as the number of transistors. Now let us say there's a representation called the block sphere representation of these qubits. We are working with a two-state system. If I have a sphere of radius unity, and I define a vector from the center to the North Pole as my 0 state, and center to the South Pole as 1 state, now I can have vectors defining anywhere, any point on the surface of the sphere. So that's a different state, and that is the superposition between these two states, 0 and 1. And it's usually written like this: cosine theta by 2, 0, plus e to the power I phi sine theta by 2, 0. Now, when we start some computing, we have to start by initializing my qubit. That means, say, initially I want to start with 0 state. There is no 1. That means if I make theta equal to 0, this is 1. So I have this 0 state, and this becomes 0. So 1 state is not occupied. Only 0 state is occupied. And then afterwards, we make different operations like quantum gates to carry out the calculations. The block sphere is in Hilbert space. But before I go into those operations, how does one implement a physical qubit? There are various ways a quantum system can be fabricated. That means a qubit can be made using different quantum processors or quantum computers. For example, I gave an example of atoms. I can use two lowest state of an atom. This is an angstrom level, the size. If I use a cluster of atoms, and you know that this can be represented in quantum mechanics by a particle in a box. Electron is confined within this. So the solution, you know that you can use these lowest two states to generate my quantum bit or qubit. Also, it is possible to use macroscopic system, large system like superconductors. Superconductor itself is a macroscopic quantum system. We can make some artificial circuits with superconductors that would behave like an atoms, like discrete states there. So how do you make quantum computers using superconductors? Basically, what you have to do, you have to make an LC circuit using materials, superconducting materials. And you know that an LC circuit behaves like a simple harmonic oscillator, and its natural frequency is given by 1 over square root of LC. This is the angular frequency, 2 pi f, omega equal to 2 pi f. F is the normal frequency. So we have to make discrete energy levels to make a quantum harmonic oscillator. So if you pick up this an L and C from your electronics lab, this would be millihenry, this would be microfarad. Then omega, the corresponding frequency, becomes about a kilohertz. That means the kilohertz separation between energy levels is very small. It would be like a classical harmonic oscillator. Now, if I use instead of millihenry, nanohenry, and instead of microfarad, picofarad, then this omega would be much larger. That means frequency would be in the gigahertz regime. Then the energy levels would be discrete. I can get a quantum harmonic oscillator. And then we can choose the lowest two states to choose our. So this is my quantum harmonic oscillator. I can now work with the lowest two states to make my qubit. But there is a problem. My qubit, I have to operate by sending microwave pulses from outside. So what you do is send microwave pulses to the frequency that corresponds to this energy difference. Now, if you look at that, this energy difference is also same. So if I want to play with these two, but if the frequency energy levels are same, then accidentally this may go from here to here or here to here, which is unwanted. So what we do in this case, we replace this linear inductor by another inductor which is nonlinear, which is Josephson junction. I'll explain what it is. With that, we can make an anharmonic oscillator. Then the energy level are not equally spaced. Now, if I choose a frequency for microwave equivalent to this energy level, I cannot accidentally excite any of these. Then I can work peacefully with the lowest two energy levels. So what is Josephson junction? It's actually superconductors, and in between it's a very thin insulator. like I explained, electron tunneling. In this case, the carriers are not electrons, it's a Cooper pairs. It's a Cooper pair tunneling through this insulating thin film, which is about 2 nanometer thickness, very thin. And that's how we can get a Josephson junction. And if we make an LC circuit with a Josephson junction, then I get an harmonic oscillator, and you work with the lowest two states. And I send microwave signal with omega, H cross omega corresponds to this energy difference. Then we can work out everything that we need to do for setting up a quantum computer. But now there's one problem, that if you leave it at room temperature, then you can say from Boltzmann distribution, you can calculate at room temperature, the occupation probability of all these levels, even n equal to 100, would be almost the same. So you are not working with just two levels. So what you have to do, you have to cool it down to very low temperature, very close to absolute zero. Absolute zero is minus 273.15 degrees C. We cool it down to minus 273.14 degrees C. That means just 0.01 degree above absolute zero, which is called 10 millikelvin in a device called dilution refrigerator. Outside is 300 Kelvin, but at these different stages it goes down, and here is 10 millikelvin. So now I give a glimpse of the development of a quantum computer in our laboratory. This is a dilution refrigerator in one of IBM's superconducting quantum computer. This is in our lab. So dilution refrigerator was initially, when you set it up, 7.6 millikelvin. We integrated electronics that works at low temperature. All these connections are there. Then we attached at the lowest bottom plate here the quantum processor, which is 1 qubit processor, which is inside. And this cylindrical things, that is a magnetic shield. Even Earth's magnetic field disturbs it. So you have to shield it. Then inside that, there's a box like that. So I'll open up this box and show you what is inside. It is a cavity here. This is cavity produces a standing wave, the microwave field. That means you get photons confined there. And this is the qubit, these little things here. So that's the qubit. And what is it? It's these plates are capacitors, and this is the Josephson junction here that produces my LC circuit. And actually, the Josephson junction is very small. It's about 30 nanometer size. And this is the Josephson junction here. And this is the capacitor. And the cavity itself is a resonator, which is this represented by this equivalent circuit. And so when it is built up, set up, it is like that. When it is covered, it looks like this. Now we have the electronics here that, so yeah. So this is the electronics. The microwave supplies goes from here all the way to the top of this, and through the connections, it goes to the qubit at the low temperature plate there. So what are the challenges of building large-scale quantum computer? So you know that this is a classical computer. This is a quantum computer. Classical computer also has gates. Quantum computer also has quantum gates. But the challenge is that these quantum gate operations you have to set up using quantum bits. And classical gates are with transistors. So one of the challenges that I'll mention a little bit later, the first thing is that how do you produce these gates, quantum gates? I go through that. You have all studied this time-dependent Schrödinger equation. This is, you're familiar with the notation of I. The I and J is the same, square root of -1. This is the Schrödinger equation, time-dependent. So the solution is that the state at time t, and if you know the state at time t0, so what you have to do, you have to integrate this from t0 to t, this Hamiltonian, and how long you apply this Hamiltonian, that means delta t equal to t0 to t. And this whole thing is called an operator, unitary operator. This operates on the state at time t equal to t0, and then you get the state at time t equal to t. So this operator is a quantum gate. And how do you produce that? Let me take a simple single qubit Hamiltonian, which is like a Pauli operator, sigma x, sigma y, sigma z. These are Pauli operator. Now say I have to construct a gate, unitary operator here, right? So that means that unitary operator is this, which means I have my Hamiltonian, but how long the Hamiltonian works? This integration has to be there to generate my gate, quantum gate, right? So this is my qubit. So if we say that I initialized it to 0 state, that means this is 0 here. So I start with the state vector in this direction in the North Pole. And now I operate with a sigma y operator, Pauli operator, which actually means a rotation around the y-axis, rotation around y-axis. Now you know that if I rotate for a small time, the quantum state comes here, 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 here. And then if I rotate for a particular time, it can come here. So that means I can take it from 0 to 1 by operating this sigma y for a particular duration of time. This is equivalent to a quantum NOT gate. Classically, you know that NOT gate, how it operates. And this is a quantum NOT gate. And this operator, this unitary operator is represented by this. So, but if I just rotate this state by up to this 90 degree, so this is still in equal superposition. If this theta is 90, this probability and these are same, equal superposition between 0 and 1 state. And this gate is called Hadamard gate in quantum operation. And this is represented by this unitary operator. This is how the gates are implemented in quantum computation. Now look at one thing here. What are the difficulties that one comes across? If you keep on operating that means with time, what will happen? This will oscillate between probability between 0 and 1, right? But it doesn't go on forever. That's the problem. These are called the Rabi oscillation. Experimentally, we measured that. What is the reason? Because in classical, the information can be retained almost forever because it's the transistor. If you keep it an on state or off state, it can stay there forever. But the quantum systems are very fragile. When it interacts with its environment, it decays. So information can be retained only for a very short time. That is the difficulty. That's the challenge in quantum computation. So how long does the qubit stay in the quantum state? This is a pictorial representation that with time, the quantum state fades away. That we can measure how fast it fades away. Oh, sorry. So this is like I mentioned about that we apply these microwave pulses and the duration decides how much we have rotated the quantum state. So experimentally, with time, you would see that the Rabi oscillation goes like this, decays with time. And from that decay pattern, we can determine is the lifetime of the qubit. And this is what we have done for these are the Rabi oscillations. You can already see that this is gradually reducing. So you can carry out this experiment for a longer time, and we can find this decay pattern. You can carry out an exponential fit, and we find that the lifetime here is 13 microseconds. Now compare this with Google Sycamore, the first quantum chip that I showed with 53 qubit. Their qubit lifetime was about 20 microseconds. The second more powerful chip that I showed, there the qubit lifetime was about 100 microseconds. This is the problem with making a larger quantum computer. That's the big challenge. So that's why still they are confined to about 100 qubit. So we carry out all sorts of other characterization. This is called Ramsey interferometry. This is called the Hahn echo measurements, all these things. And we also carry out interaction between photons in the cavity and qubit. Qubit is just like an artificial atom. You know the photon-atom interactions that is represented by the quantum electrodynamics. So from experimentally, we can actually determine the strength of this interaction. So this is, for example, the resonance frequency of the cavity, which is without interaction with qubit, it is somewhere here. But if it interacts with the qubit, if the qubit is in 0 state, this frequency shifts to higher frequency. If the qubit is in 1 state, it shifts to the lower frequency. So from this shift, we can calculate the coupling strength between the cavity photon and the qubit. So you can do lots of basic quantum mechanics with this. Now we are transitioning to 5-qubit measurements, and pretty soon we'll start with the 5-qubit measurement. A superconducting quantum chip with 5 qubits. Now I come to the conclusions. So conclusions are not just a few statements, it's a timeline of the development of classical computer vis-a-vis quantum computer. As I mentioned, the predecessor of transistor was vacuum tube. So you can say starting from here, since today, it took almost a century to come to this stage of the classical computer. And the quantum computer is just about 3 decades. 1981, the idea was proposed for the quantum simulator. And then a 5-qubit quantum computer was developed by IBM in 2016 only. Now we have in the whole world about 100-qubit quantum computer. So quantum computing is transitioning from scientific curiosity to technical reality. Advancing from discovery of useful machines takes time and engineering. We must be in the game to play. So we are still playing the game to improve the qualities of quantum computer. Now, there are many companies in play. This is the Google I mentioned. This is the Rigetti. They are also superconducting quantum computer. There's a company called IonQ. They use trapped ion qubits. There's a Continuum. They also use trapped ion qubits. D-Wave, this also uses superconducting qubit processors. But among all these things, if we compare, this is the Wright brothers plane that you see here. So if we compare today's plane, most sophisticated Dreamliner plane, and compare that with Wright brothers plane. So as far as quantum computer goes, we are not far ahead of this Wright brothers plane. So we are still baby. So we are trying to develop things, but already glimpse of great hopes are there that has been demonstrated. So we do not yet know all of the applications that the second quantum revolution will bring, but we anticipate they could be as revolutionary as the first one or even more. When practical large-scale quantum computers are built, how much time I have? About 5 minutes or?
You can actually go until, well, anywhere between up to 10 minutes is fine also.
Okay, so then I'll elaborate on some of this. I'm in the concluding part, but I can elaborate on these things.
Okay.
So when practical large-scale quantum computers are built, it would enable drastic progression in drug discovery and development. So how do you discover drug these days? For example, for any disease or whatever. So what is done, some prospective molecules are taken and then computations are done on that using supercomputers, for example, classical computers. And then maybe it closes down to several thousand or several 100,000 molecules. So then they ask the laboratory person, the experimentalist, to try it out in the laboratory. So if you have to try 100,000, it takes a lot of time. So drug discovery takes time. But what would quantum computers would be able to do? They would be able to bring it down to only say tens or even hundreds of possible molecules. Those are the potential drugs. So in that case, in the laboratory, you don't have to try to do experiments on many molecules. A fewer sample of molecules you have to try. And that's how drug discovery would be much faster. And the drug development should be much faster. And then designing new catalysis to efficiently synthesize chemicals such as fertilizers. So for fertilizers, it's also trial to develop a good fertilizer. So now if you can carry out the calculation for potential molecules, and if the number is not very large, then their catalytic activities can be tried in the laboratory. That means only on a fewer molecules or fewer systems. That will actually expedite the even discovery of new fertilizer, very effective fertilizer. Development of new materials by manipulation of physical or genetic properties. In many biological systems, actually, this quantum, what I mentioned, this superposition and entanglement. they take place. This quantum phenomena takes place in many biological systems. In fact, about a month back, or 1.5 months back, IIT Kharagpur, their SMST department, they wanted to open a department for quantum biology. They had a research scholar seminar. They invited me to give a talk. I gave a talk on quantum biology. There are even many processes take place at the quantum level, like photosynthesis and many things else. So inherently, there all these quantum principles, superposition and entanglement, they take place. And I must tell you that the whole universe is fundamentally quantum. So even in our human body, in the DNA strand, within the two strands, the proton can tunnel, quantum tunnel from one to the other. And that causes mutation. And that eventually causes aging and even tumor. So the quantum phenomena is taking place in the whole of the universe, including biological systems. So one can modify genetic properties using the quantum computation or the physical properties. Say, for example, today, superconductors, you don't have any superconductor at room temperature, right? So if you could get superconductors at room temperature, we can make our transmission line for electricity with those wires, then there will be no power loss. Imagine that. Without any energy loss, we'd be able to use electricity in the transmission, there would be no loss. So to find a superconductor which would work at room temperature, we need to try out many calculations. And this can be possibly done with a quantum computer to predict which material would give us room temperature superconductivity. And then to solve complex optimization problems of great commercial importance, such as scheduling logistics, like the traveling salesman, how it maximizes its gain by choosing the optimum path, scheduling said the flights, etc. Traffic congestion, what would be the optimum route for less traffic congestion, less fuel consumption, all these things, fraud detection, and in stock portfolio. We'll tell you that which portfolio would be more economical or more profitable. All these things can be predicted using quantum computation. Address fundamental science questions in nuclear physics, high energy physics, and many other fields. These are huge possibilities that are waiting in front of us with quantum computation. Now, these are two QR codes I have shown here. This is American Physical Society TV made a video on our center, and they actually had shown it in APS March meeting in 2023 and 24. So with this QR code, you can see this video. And about a month back, DD Bangla showed a program on our center, TCG Crest. There also you can see a glimpse of this quantum computer, how things are being done in our center. But we are also working on quantum materials for superior superconducting qubits. You know that the qubits, their coherence time, lifetime is short. There is a possibility that another material, aluminum is used, superconducting material is aluminum, aluminum oxide is the insulator, another aluminum that is used to make the Josephson junction. There is a possibility that another superconductor, cobalt disilicide, would be able to give us Josephson junctions and qubits with a much longer lifetime. And just it's available online already, our recent work, two superconducting thin film systems with potential integration of different quantum functionalities. So with cobalt disilicide and cobalt 2 materials we present in this work. It's in the journal Materials for Quantum Technology. It's an open access journal of Institute of Physics, UK. So you can have a look at that if you like. Now, before I thank, this is the team. This is Dr. Snehal Mondal. He was a postdoctoral fellow, but now he's an assistant professor. And Biplav Biswas and Ayan Ghosh, they are two PhD students. And this is the eternal student working in the lab. And thank you for your attention.
Thank you very much, Professor Dev, for a very informative and illuminating talk. I would request maybe you can allow 5 minutes for any questions that the participants may like to ask.
Yeah, sure, sure. I think there's a provision for 10 minutes per question.
Yeah, well, because we're running a bit late, maybe
Okay,
5 minutes, at least 5 minutes.
Okay, no problem. No problem.
Yeah. Okay, I don't see any question in the chat box. I've tried, asked for questions there. Any student? Questions about the quantum computer and quantum technology that we heard about? Well, I would say that, well, having a quantum computer in
Someone raised a hand. Vinod Gupta raised a hand.
as good. Okay, then go ahead, unmute yourself and ask the question. Vinod Gupta, please go ahead, unmute yourself and ask the question. What happened?
Maybe he could not unmute. I don't know.
No, yeah, it's very simple to unmute. Just click on the audio.
But if it is controlled from the center there,
well, then the IT central.
If it is muted from control center, then they
I
cannot.
think he has been able to. Okay, go ahead and speak.
Sir, you said that these qubits changes their states quickly.
Yeah,
so
if you keep them isolated, no interaction with any environment, then they can stay for a very long time. But they interact with the environment, and that's how they lose their quantumness.
So, in quantum computers, we may have a set of solutions in place of a single solution as compared to classical computers.
Yeah, that's why I mentioned, if you remember, that is the same measurement, the same calculation you have to carry out, say, 1 million times or so, then statistically you will get your answer.
Okay.
Just one measurement will not give you answer. You will get wrong answer, perhaps. Like if you throw a coin, and if you expect a head, you may not get head. You may get, because it is probabilistic. So one measurement will not do. If I want to carry out a measurement, measure the qubit state at the end after the gate operations, I have to, under the same condition, I have to initialize this qubit and then repeat the same thing, maybe 10,000 times or 1 million times. And then the results would be average, right? Like a head or tail, if you throw 1,000 times, about 500 times you get head, about 500 times you get tail, right? But if your quantum state has the probability giving a result like out of 1,000 times, you expect it to get 700 times state 1 and 300 times state 0. That you will get only after you have carried out so many experiments.
So after a long number of calculations, we will arrive at a certain conclusion.
Right. But this computation takes very short time.
Okay, thank you.
Yeah, well, I should read out a question sent by Professor Dashgupta. Would it be possible for the students to visit TCG Crest and see the system?
Yeah, sure.
My question also, because I personally would like to see, but the students are more important.
Sure.
Can make a visit.
Yeah, welcome to visit and see.
Okay, so then contact you and make arrangements and then finally visit convenient time.
Okay.
Okay, thank you. Any other question from the audience? Anyone else? Then we will close the session. with another, again, I thank you, Professor Dev. It was a wonderful lecture, and it is so interesting to have a quantum computer here in our city of Kolkata. We are very, very proud of it. Thank you.
Thank you. Thank you.
Thank you very much.
Shall I stop sharing? Shall I stop sharing? No, you are talking, but I can't hear you.
Oh, sorry, I muted myself. Yeah, if you have the time, do continue with us, and we'll continue with the next lecture now.
Okay.
Thank you.
Yeah.
We are inviting Professor Ananda Dasgupta of Indian Institute of Science, Engineering and Research as our next lecturer. I would like to say a few words to introduce him to our audience. He's rather reticent about himself, so I have very few words to tell him. He did his PhD from Jadavpur University in 2001 and started his academic professional career at St. Xavier's College. Then he moved on to Jadavpur University and finally to Indian Institute of Science, Engineering and Research. And there he's a full professor now. His area of interest in research is investigation of singularities or their avoidance by means of the Raychaudhuri equations in general relativity or other gravity theories, use of a mean field approach to study phase transition in liquid crystals, algebraic techniques in the field of quantum optics, especially in squeeze states and matter radiation interaction. In addition to being a researcher, Professor Dasgupta is a committed teacher of physics. And I'd like to say that he moves very easily from one area of physics to another. And he is a great communicator and presents the topic very lucidly through his YouTube channel for the students and also for anyone who wants to know about the subject. So I have, followed one or two topics there also. He received INSA Teacher Award in 2023, and he's our Vice President of IAPT RC 15, Professor Ananda Dasgupta. And before he starts, I would like to just say that Dr. Minal Kanti Pal has asked for a question, but that I will answer separately. Professor Dasgupta. I think Professor Dasgupta can unmute yourself. I mean, can you not unmute yourself? Oh, the system, the IPT Central. I request IPT Central.
Okay, I think now I can unmute myself.
Okay, right. Good.
Can you hear me clearly now?
We can hear you, but you have to share your screen and so on.
Yeah, I will do that. That's fine. But
we can hear you.
Okay. So first, host has disabled participant screen sharing. So I have to be able to screen share, which I can't do right now until the permission is given.
So again,
now,
IPT Central, yeah, you can do it now.
Now I can. I guess now I can.
Yes, now you can.
Yeah. I think what I will do is I will just share one. I think this window should be enough. Let's see.
No.
Can you see a window with
I can, but it is very small and you have to make it full screen anyway. You don't, that way we'll be able to see
already full screen for me, but let's see.
No, we are looking at the entire, like all your series of slides we can see.
Okay, wait a minute. Can't even control. Sorry, until and unless, okay. Let's do one thing.
Yes.
Let's stop this share. I will share the entire screen. Okay. Then maybe it might work. I'm not very used to using Zoom. But anyway, let's see. Share. One per participant can share at a time. That's what I'm doing. But
There are
let's-
3 choices. When you want to share, there will be 3
Yeah,
choices.
I think there should be a full screen choice. Desktop one. That should be the one, right?
We'll try it out.
Can you see my desktop right now?
No, I still see it as a small window. It's not coming the full thing.
Okay, let's see. It's not even allowing me. So has it gone blank now, or can you
No,
still
no,
see
it's
it?
showing the Zoom. It's showing the Zoom screen,
Hmm.
but not your slides.
Strange, because
Yeah,
Yes.
now the slide is here, but the slide is not full screen.
yeah, I deliberately stopped it from being full screen, but now okay, I think this should be okay now.
If
Let's
you
see. Yeah,
minimize the zooms, and now
should
it's,
it be okay? Hmm,
yeah, now it's good.
Right.
Yeah.
Hmm.
But still it is not, I mean, when we look at it, it's not like, 50% of my screen. It is still like one window.
No, I think that is something you should be able to change, because
Okay,
I
then
have a full
IPT
screen.
Central, please help.
I have a full screen here.
Yeah,
I can't really do anything else about that. Oops.
please help IPT Central because they are managing it.
So what's the situation now?
Um,
Any improvement, or?
it's bigger, but I can see only part of your screen. It's not full. It's a vertical screen, not a not a.
Why should it be vertical? Mine is, I'm doing this from the laptop, so
Yes,
but I
certainly.
can't see your. Actually, I can't see what you are seeing on Zoom. I can only see my own screen right now.
I understand.
So I can't really help there.
Now I can see the better way. Now it's
But then I
better.
will just make it full screen
Yeah,
now.
yeah. If you minimize the zoom and have that your presentation full screen, then it will be okay because the zoom was full. Now your screen is visible.
Okay, now I think it should work.
Yeah, participants are saying that it's okay for them. Yes.
Yeah, now it's
Yeah.
okay. Now
Yeah.
it's okay.
Okay. Thank you for the kind introduction. And I should, of course, thank the organizers. That's the usual form. That's what we usually do. However, in this case, I think it will be a bit of a side goal for me to thank the organizers. So, of course, yeah, the actual organizers of this have done a wonderful job over the last 3 sessions that has happened. Now, I am feeling rather reticent about my presentation after the previous one for several reasons. One of them is I planned this more like a classroom lecture rather than a sort of overview thing. The great overview that you just heard a while ago, my lecture is not really going to be like that. It has, in fact, I just counted. I have no pictures. Okay, sorry, I do have one picture, the very dim background that you can see on the title page right now. But apart from that, I have 0 pictures and a lot of equations. So I hope it will not be too much of a burden on the audience. And I'm assuming that there are enough students in the audience to at least appreciate having some kind of a classroom lecture. So having said that, that was an apology in advance. Having said that, let me stress that today we are going to talk about primarily coherent states. In fact, not everything about coherent states, only a small subpart of that. And if we have time near the end, we will talk a bit about squeeze states as well. So, and once again, let me also stress that the subject of coherent states is a huge and varied topic. So we are only going to confine ourselves to a rather small subpart of that. But before we go there, let us just try to see why we are looking at coherent states at all. And for that, we should take a look at this, that there are three different distinct questions that we will try to ask first, and then answer these questions. And we will see that coherent states play a very important role in the answer to all of these three questions. Now, the first question that we are going to ask is about the uncertainty principle. Now, this is something which all of you are definitely very familiar with. As you know, uncertainty principle is one of the cornerstones of quantum mechanics. And in one dimension, the position momentum uncertainty principle takes this rather well-known form. Delta x times delta p, the variance in x times the uncertainty in the momentum, the product exceeds h cross by 2. Note that this is an inequality. It doesn't say how much bigger than h cross by 2 this product can be, but it does say that the product of the two uncertainties in these two conjugate variables cannot be less than h cross by 2. The question that we have naturally at this stage is, can we actually achieve this lower bound? That is, can we get to h cross by 2? And I'm pretty sure many of you know the answer, at least partially. You know that the ground state for a harmonic oscillator does have the correct uncertainty bound. That is, if a particle is in the ground state of a harmonic oscillator, then its uncertainty product for position and momentum is exactly equal to h cross by 2. But are there other possibilities, more general ones? And can you, in a certain sense, do better? Of course, we will explain what that sense is later on. Now, our second question is a question about limits. More precisely, the limit of quantum mechanics in which it becomes, quote unquote, classical mechanics. Now, many of you may already be familiar with this quote. This is from Dirac's famous textbook, that classical mechanics may be regarded as a limiting case of quantum mechanics when Planck's constant h by 2 pi tends to 0. Now, in reality, things are really not that straightforward. For example, there are plenty of situations where this kind of classical limit cannot be taken at all, or if they can be taken only in a very specific way. Just to cite one example, if you look at the total scattering cross-section from a hard sphere of radius r, the classical result is very straightforward. Classically, when you look at a hard sphere head-on, you get to see its cross-section, which is just a circle of radius r. And so the total scattering cross-section, in this case, for hard spheres is simply pi times r square. On the other hand, the quantum result, at least in a simple low-energy limit, is exactly 4 times that. Taking h cross to 0 does not change that at all. In a sense, it seems like the wave nature of the particles being scattered allows them to sort of scan the entire surface of the sphere, not just look at the cross-section, which is why you can sort of understand why there's a factor of 4. But notice that in this case, no matter what limit you take, you are not going to get the classical result back. Well, a situation where things are slightly more clear-cut, at least apparently, is that of time evolution, sorry, that's a typo, and I did the wrong thing. It's a time evolution that we are talking about. Time evolution of expectation values. Well, once again, most students would be aware that Ehrenfest's theorem apparently answers that in the positive. Just to remind you, we start from Schrodinger's equation. You can get these results about the expectation values of position and momentum. Rate at which the position's expectation value changes is equal to the momentum divided by mass. Rate at which the momentum's expectation value changes is given by the expectation value of the negative of del V del X, which of course, as you're all aware, is the force. And sticking to one dimension for this, you can have multidimensional extensions of this result. Now, this looks exactly like the classical equations. In classical physics, we know that the rate at which position changes is momentum by m. That's, of course, the definition of momentum, mass times velocity. And the rate at which momentum changes is minus dv dx, del v del x, which is just the force, Newton's second law. So it looks, at least on the face of it, like the fact that this equation, ddt of expression value of x is expression of p by m, and the second one exactly mimics the classical equations. The real question is, do they really? And to see that the answer is not really yes, let us take an example. Suppose we talk about the quartic and harmonic oscillator, where the potential is x to the power 4, unlike our familiar harmonic oscillator, where of course the potential is proportional to x squared. Now, in this case, if you use the Ehrenfest theorem, the left-hand equation, of course, stays the same. It's independent of the potential. The right-hand one tells you that the rate at which the momentum changes, or rather the momentum expectation value changes, is minus lambda times the expectation value of x cubed. Now, let's look at the classical formula. The classical formula, as expected, looks exactly the same, except for the fact that in the quantum formula, you have expectation values. In the classical formula, you have actually x and p, the variables. However, there is one big catch. Here you have lambda times the expectation value of x cubed, which is not the same. Despite the fact that this looks like expectation value of x and expectation value of p obeys the same equations on x and p, expectation value of x cubed, which is there on the right-hand side of the rate of change equation for the momentum expectation value, is not the same as the cube of the expectation value of x. And as a result, these two are different equations. If the equation for the expectation value of p had been d dt of expectation value of p is minus lambda expectation value of x whole cubed, then of course there would be no problem at all. But here, they are really different equations. So even Ehrenfest theorem, which apparently tells you that the classical equations for excitation values exactly match, the quantum equations for excitation values exactly match the classical equations, don't really say that. There is one exception, however, and that's a very important exception for us, which is the harmonic oscillator. For the harmonic oscillator, the potential is quadratic. And hence, the equations which Ehrenfest theorem gives you are actually linear equations. ddt of expression of x is, of course, as always, expression of p by m, but ddt of expression of p is simply minus m omega squared times expression of x. And now, this exactly matches the corresponding classical equations. And so, expression of x and expression of p for a harmonic oscillator, no matter what the state is, always obeys the same equations that you expect the classical formula variables to do. So expression of x at time t is expression of x at time t0 times cosine omega t minus t0 plus, this is the v by omega sine omega t minus t0 that you're all familiar with in the standard classical solution for a harmonic oscillator. And the expression of p similarly has exactly the classical evaluation formula. However, there is a big difference between classical mechanics and quantum mechanics, even for the harmonic oscillator. And what is that? Well, for energy eigenstates, remember these are stationary states. In stationary states, things don't evolve with time. So expression value of x at time t stays whatever it was at time t0, namely 0. And the momentum expression value also vanishes. Again, a result which should not be unfamiliar to any of you. But we just found that the expectation values for harmonic oscillators, eigenstates, whichever states you are talking about, would always oscillate with frequency omega. However, this is not really inconsistent with that result. This is consistent with the classical behavior After all, if you do not disturb a harmonic oscillator from its equilibrium position, then its position and momentum stay zero at all times. So there is nothing really non-classical about these results. Of course, these are results for the expectation values for quantum systems. But as we have just said, Ehrenfest's theorem guarantees that for the harmonic oscillator, the classical values will be obeyed. They are obeyed here too. However, this will completely defy the classical connection that we know between the amplitude of the motion and the energy of the motion. We know that the energy of the motion, which is entirely potential when the particle is at one end of its motion, is given by half m omega squared a squared. There is no kinetic energy at the end point. Total energy is just exactly equal to the potential energy there. So that's what we have. Notice that when you are in a harmonic oscillator eigenstate, the nth energy eigenstate has an energy given by n plus half h cross omega, which can be pretty large when n becomes large, pretty large compared to, say, other quantum systems, I mean. But the amplitude of the oscillation is still zero. So this equation, the classical equation between energy and amplitude, is not valid at all. The gap between the two, E minus half m omega squared a squared, among the energy eigenstates is closest for the ground state, simply because the energy is the smallest there. Half m omega squared a squared is still zero. E for the ground state, where n is zero, is of course half h cross omega. So this is the smallest you can have among energy eigenstates. The closest energy gets to half m omega squared a squared. The question that we are asking here about this limit, where the classical theory behaves the same way as quantum theory, would be, can we get closer? That is, can we make this gap smaller than half h cross omega for a harmonic oscillator? And can we do that when the amplitude is not zero? We can do this for the ground state, but then the amplitude will be zero. So the expectation value of x and expectation value of p will not change with time at all. The question is, can we have time varying solutions for expectation value of x and expectation value of p, where we can come at least as close as this, or maybe closer? So that is our second question. And the third question that we are going to address is something that I'm going to call the eigenstate question. Now, once again, everybody here knows that for an operator O, a state psi is called an eigenstate of O. If for some lambda belonging to complex numbers, which I should have mentioned here, I think there's a tech typo again, we have operator O acting on psi is lambda times psi. Now, I'm assuming that everybody is more or less familiar with the bracket notation. If you are not, some of the students may not be. If you're not, then just mentally replace the ket psi, this object sitting to the right of O, by the wave function psi. At least since we are only going to talk about one-dimensional harmonic oscillator here, that is not going to be much of a problem. Now, lambda is called the correct corresponding eigenvalue. And as you, again, I'm pretty sure everybody is familiar with this, eigenstates and eigenvalues play a central role in quantum mechanics. For an observable A, the eigenvalues are possible results of measurement. And once you do a measurement and get one of those eigenvalues for sure, the post-measurement state would be an eigenstate. There can be complications if your measurement is not perfect and so on. We are not going to go into that right now. Now, observables in quantum mechanics are represented by Hermitian, more precisely self-adjoint operators. Now, can non-Hermitian operators have eigenstates? That's an important question. In particular, since we are talking about the harmonic oscillator, there are two non-Hermitian operators which play a very important role. We know that they are non-Hermitian because they're adjoints of each other and, of course, not the same. The raising and lowering operators, A and A dagger, can they have eigenstates? So that's our third question. Now, before I go into the answer, I will very quickly go through some basic results about the harmonic oscillator, which again may be redundant, but I'm going to go a bit fast. If anybody has any questions about that, please raise your hands and let me know. Or I'm not sure whether I can see the raised hand. I don't think I can, but somebody will be able to see the raised hand and let me know. So this is a lightning review of the harmonic oscillator, which takes this form. Hamiltonian operator is p squared by twice m plus half m omega squared x squared. Exactly the classical form quantized for in general. And in the position picture, we know that p can be replaced by this differential operator, and the Hamiltonian operator looks like minus h cross square by twice m del 2 del x2 plus half m omega square x square, where the operator for x in the position picture is just multiply by x. So if we now introduce the lowering and raising operators, which are basically x plus ip by m omega and x minus ip by m omega, apart from two factors which are chosen essentially to ensure that the commutator bracket of A and A dagger is 1, we end up with this Hamiltonian, which now becomes h cross omega A dagger A plus half. And A dagger A is our favorite number operator. As we will see, it's called the number operator because it can only have eigenvalues, which are natural numbers. This form, of course, implies that any eigenstate of number operator is also an eigenstate of the Hamiltonian. So if n acting on a state ket n gives you n times ket n. Again, if you're not familiar with the bracket notation, just substitute psi n for ket n. Then Hamiltonian acting on the same ket n will be h cross omega n plus half ket n. So if you know the eigenvalues for capital N, you know the eigenvalues for the Hamiltonian. Now, the most important result for us is that the commutator brackets of n with A and A dagger are very, very simple. That of n with A is minus A, and n with A dagger is plus A dagger. And it is this property which allows you to conclude that if A, the operator, were to act on an eigenket of n with eigenvalues n, it is going to reduce the eigenvalue by 1. And A dagger similarly is going to raise the eigenvalue by 1. And I'm pretty sure all of you are, or at least most of you have seen these equations, that A acting on ket n gives you ket n minus 1, and A dagger acting on ket n gives you ket n plus 1. These are normalization factors which ensure that both ket n and ket n minus 1, or ket n plus 1 as the case may be, end up being normalized to unity. Now, the important thing is, if I keep on hitting an eigenstate with A, the eigenvalue n goes down by 1 every time. But the Hamiltonian H, being the sum of two squares of Hermitian operators, p square and x square, with positive coefficients, must have only positive eigenvalues. And that means that this lowering cannot continue forever. It must be bounded below. And the only way this can be bounded below is that there must be a state, which I'm going to call ket 0, on which the operator A acts and gives you 0 and not a new eigenstate, not an eigenstate corresponding to eigenvalue minus 1. And once you have this, from this state, you should be able to get to any eigenstate by keeping on applying A dagger. And that tells you that the possible values for the eigenvalues of capital N must be non-negative integers, 0, 1, 2, 3, and so on. And this is one result that we are going to need. If you just keep on applying A dagger on the state 0, you get A dagger acting on ket 0 once to be ket 1, then A dagger acting on ket 1 gives you ket 2 by root 2, and so on. If you just repeat that small n times, you end up with the ket n being A dagger raised to ket n to the power n by square root of n factorial, this operator acting on ket 0. Now, I'm pretty sure this last lightning introduction was not really very important because all of you already knew that, but still, some of you may have forgotten. And now, with this under our belt, we are going to try to understand the solutions to the questions that I had raised. So at this stage, are there any questions? Because if there are, I can pause and answer them now. But of course, I'm going to actually answer the question that I've raised one by one. So assuming that there are no pressing questions right now, let me get to the answer to the eigenstate question first. That is, can the raising and lowering operators have eigenstates? So what we are trying to do is find the lowering operator eigenstate, a state denoted ket alpha, on which the lowering operator A acts, and you get alpha times ket alpha, a number alpha times ket alpha. Well, we know that the harmonic oscillator energy eigenstates, ket 0, ket 1, ket 2, etc., the number eigenstates that we have been just talking about, they form a complete set. That means you can expand any state with some coefficients A0, A1, A2 in terms of this ket 0, ket 1, ket 2, etc. This is, of course, in general, an infinite expansion. And if ket alpha is to be normalized, then A0 square, mod square plus A1 mod square plus A2 mod square, etc., this sum has to be 1. We will worry about normalization later. Let's just first take a look at what happens when you take this state ket alpha and apply A on it. Well, A being a linear operator ignores these coefficients and goes and hits the kets. So you have A0 on which is skipped over, and A acts on the ket 0, AX on the ket 1, AX on the ket 2, and so on. And just by using the fact that A acting on ket 0 is 0 times 0, A acting on ket 1 is square root of 1 times ket 1, A acting on ket 2 is square root of 2 times ket 1, sorry, A acting on ket 1 is square root of 1 times ket 0, A acting on ket 2 is square root of 2 times ket 1, and so on. We get this, which can be written down in this form, in this infinite sum form. Now, what we are demanding is that this particular ket that we have found out, A1 square root 1, ket 0, etc., must be alpha times this. That is the original ket alpha. Now, the only way that can happen is that the ket 0 coefficient of A acting on ket alpha must match the ket 0 coefficient of alpha times the number alpha, and so on. So this can only happen if you just keep on matching the coefficients of the various basis kets here. A1 times root 1 has to be alpha A0, A2 times root 2 has to be alpha A1, A3 times root 3 has to be alpha A2, and so on. In general, An times root n has to be alpha An minus 1. And what that means, if you solve this, it's pretty simple, that An has to be alpha raised to n by square root of n factorial times A0. So we have managed to figure out all the coefficients, A1, A2, A3, all the way up to A infinity, or An for any n, in terms of the one coefficient A0. And that means we have found our eigenket. The ket alpha is this overall A0 times this infinite sum, alpha to the n by root n factorial ket n. This is an infinite sum, but of course, in practice, we need only go up to some sufficiently large n so that this 1 by root n factorial in the denominator will cut everything down. We can normalize A0. Again, that's a very simple calculation. I'm just going to skip over that for want of time. But once you normalize this, it's a pretty straightforward summation. And okay, I have the privilege of addressing a few students, I expect, so I'm going to leave that as an exercise for them. The normalized ket alpha is simply this same sum. It is above minus alpha mod square over 2. That's the normalizing factor. Now, this state is called a coherent state. So we have met the hero of our talk rather late, midway into the talk. An eigenstate of the lowering operator belonging to the eigenvalue alpha is called a coherent state. Why is this called a coherent state? We will get a glimpse of that at the end of this lecture. For the time being, let's just take that as nomenclature. The eigenvalue alpha can be any complex number. Of course, all of you know that for Hermitian operators, the eigenvalues can only be real, but A is not, the lowering operator is not Hermitian. and its eigenvalue can be any complex number whatsoever. Now, quickly, for those more familiar with the position picture, the operator A in the abstract form looks like this, but I can always replace the operator in the position picture by h cross over I ddx. So in the position picture, it takes the form given by this. So if you want to find out the eigenvalue or eigenvector for this operator A or an eigenfunction in the position picture, all you have to do is solve this simple differential equation. And despite the fact that it looks a bit complicated because of these m omega by h cross factors, it's really a very, very simple differential equation. It's a first order linear differential equation. And just by changing the variable to xi0 just to make the equation a bit more compact, the equation simply becomes this. d psi alpha dx is a constant times x minus xi0 times psi alpha. And this can be immediately solved by simply a host of methods. One of them would be just divide the whole thing by psi alpha and multiply by dx and integrate. And you get this solution. Now, this should be a very, very familiar solution to most of you. If you leave out the xi naught, and this, of course, is a normalized version of that. And I'm pretty sure most of you can recognize that if you leave out the xi naught, what you get is exactly the ground state wave function for a harmonic oscillator. So even the ground state wave function happens to be a state corresponding to xi naught equal to 0, that is alpha equal to 0. And what we have seen here is that the wave function for this coherent state essentially the displaced ground state. X has been shifted to x minus xi0. So the center is no longer at the origin. The peak is no longer at the origin for the wave function. The peak is displaced to a different point. Now, a natural question would be, what about the raising operator? Can we find an eigenstate for that? Can we find a state beta such that A dagger acting on beta is beta, the number times ket beta? And the answer to that is simple. We just try whatever we did right a while ago. We expand beta into harmonic oscillator eigenstates. Multiply root 1, ket 1. This is what you get from ket 0, A dagger acting on ket 0. A dagger acting on ket 1 gives you root 2 times ket 2 and so on. But we don't really need to go any further. Notice that the original ket beta had a B naught. That state is no longer there in A dagger acting on the ket beta. Since A dagger raises the eigenvalues or number eigenvalues, the ket 0 has changed under the action of A dagger to ket 1. So this one has no ket 0 component, and that tells you that this state can never be equal to beta times this state, because this will have a ket 0 component. The raising operator, unlike the lowering operator, has no eigenstate. And that may seem a bit strange because, after all, if we have to do this in the position picture, all that changes is I in the differential in front of this d hat operator changes to minus I. So you get a similar looking differential equation, just the same kind of equation that you had for the lowering operator. Why then does this not work? The answer is, if you were to solve this equation, you will again get a very similar looking solution, or you will get something which has e to the power x minus xi0 whole square with a positive sign, which means that the wave function which satisfies this eigenvalue equation will not be normalizable, will diverge to plus minus infinity when you go very far away. Not a valid solution. So both from the position picture and just by looking at the action of the raising operator, we can see that the raising operator cannot have an energy eigenfunction. So the eigenvalue question has been answered. Lowering operator has energy eigenfunctions, which are coherent states. The raising operator does not. Now, the important question is, why should we bother with eigenstates of the lowering operator, Ket alpha? After all, that's just one operator. Why should we pay so much attention to them? Well, let's look at the uncertainty question. Now, notice that if you look at A acting on Ket alpha is alpha alpha, this immediately gives us, since alpha is normalized, if we hit this with a bra alpha, for those unfamiliar with the bracket notation, this is psi alpha star operator A acting on psi alpha integrated. Simply gives you alpha because Ket alpha times Ket alpha, this number just comes out of the integral, and Ket alpha times bra alpha acting on Ket alpha is just 1. And taking the adjoint of this, we immediately get alpha A dagger alpha. This expectation value is alpha star. So operator, the raising and lowering operators both have very simple expectation values, namely alpha and the conjugate of alpha. But now, remember, we made our A and A dagger out of X and P. And we can just invert those equations to get X and P out of A and A dagger. In particular, X becomes this. And since root over H cross by twice M omega is just a numerical factor, it can come out. And you can just get the two expectation values of A and A dagger being positioned here. And therefore, this is a very simple result. Simply, X squared expectation value, well, you will need A plus A dagger whole square. Now that expands to A square plus A dagger square plus, again, as you all know, commutation is something we assume for ordinary numbers, but operators don't necessarily commute. If they don't, A and A dagger is a commutator of 1. So you cannot write A plus B whole square as A square plus B square plus twice AB, but you can write it as A square plus B square plus AB plus BA. And you end up with this, A dagger plus A dagger A. And what will make life easier for us is that you can replace the A dagger by A dagger A plus 1 from the commutation relation. So this is what you get. Now, A acting on alpha gives you alpha acting on Ket alpha. Another A acting on alpha gives you alpha square. So this will just give you alpha square. Similarly, this will give you alpha star square. This one will give you alpha, this one will give you alpha star. So basically, this is what you get. Now, the reason why I've written this in red, you may have already figured that out. Look at this expectation value for X. If you square that, what you get is exactly these terms. H cross by twice M omega, alpha square plus alpha star square plus twice alpha star alpha. What you do not get is the additional plus 1. What that means is delta X squared, which is X squared expectation value minus X expectation value whole squared, is simply given by this quantity, H cross by twice M omega. Now, a very similar calculation, which you can all carry out yourself, will give you delta P square. Exactly similar, very little change, except for the factors, get H cross M omega by 2. But when you multiply the two, note that the M omega cancels, and you get H cross square by 4. And that's for the square of delta X times the square of delta P. And that tells you that for all coherent states, delta X times delta P is exactly H cross by 2. So coherent states give you non-trivial oscillations. These are not stationary states in general, if you leave out the ground state, which of course is a very special case. All other coherent states do show expression of X and expression of P, which oscillate really, and they satisfy this uncertainty bound H cross by 2. And well, in order to make the relation even more striking, we can define dimensionless versions of capital X and capital P. If you look at these equations, delta X and delta P look a bit different. But that's simply because they're dimensional quantities with different dimensions. Of course, they will never look the same. But if you look at dimensionless quantities like this, where you have taken out this factor, which has the dimensions of position, which is simply A plus A dagger by 2, and capital P hat, which is again a dimensionless version of small p hat, which is A minus A dagger by twice I. These are very similar to X and P except for these factors, and you can easily check that their commutation relation is also very much like the canonical commutation relation IH cross for small x and small p, but because of these dimensionless factors, it has become I by 2. And the uncertainty product, which you expect for X and P, is delta X times delta P is greater than or equal to 1 by 4. This, by the way, is true for all systems, not necessarily harmonic oscillators, all one-dimensional systems. But the coherent state in particular obeys this very special result, that delta X and delta P are exactly equal and equal to half. So a coherent state not only has the minimum uncertainty product, it has the same uncertainty in the dimensionless versions of X and P. Now, before I continue, let me just ask a question to the people controlling this. How long do I have actually?
Professor Dashgupta, you have, well, you should have 1 hour in overall. So almost like another 25 minutes or 20 minutes at least. We have to close at 9 o'clock. Yeah, 20 minutes.
Then I think I should be able to sort of do justice to much of what is left.
Yeah, okay.
Okay, so let's now look at the amplitude versus energy question that we had asked. Can the energy minus half m omega squared a squared, this gap between the energy and the classical value, be reduced beyond half h cross omega? Or at least can we do this with things which are really oscillating? So if you write the energy, which is the expression value of the Hamiltonian, no, the energy is the eigenvalue of the Hamiltonian only for stationary states. For a general state, it's the expectation value of the Hamiltonian that we are using. So p squared expectation value by twice m plus half m omega squared times x squared expectation value. And on the other hand, we know for a harmonic oscillator, the expression of x at time t, this is what the Ehrenfest theorem told us, is the expression value of x at time 0 actually, cosine omega t, plus expression of p by m omega, that's the velocity at p equal to 0, times sine omega t. Again, the familiar classical oscillation formula. Now, given this, you have a cosine term and a sine term. You all know how to calculate the amplitude for that. The amplitude squared is given by this squared plus this squared. And so if you subtract half m omega square a square from E, this is my E, the first bracket, and the second bracket is minus half m omega squared times a square. Can easily see by gathering terms together that this simply becomes p expectation value squared minus p square expectation value minus p expectation value squared by twice m, plus a similar quantity with half m omega square coefficient for x. It is nothing but delta p whole square by twice m plus half m omega square delta x whole square. My next step will be exactly trivial algebra. These are, of course, numbers. Now they are no longer operators. These are just simple numbers. So we can use ordinary algebra with this. We can actually write this in this form. The sum of two squares, a square plus b square, and this I can write as delta p minus m omega delta x whole square, a minus b whole square, plus twice ab. Now notice that here we have something which can never give me a negative result. Delta p, delta x, all these are positive, are real numbers, in a positive real numbers. This can never give me a negative value. And delta x, delta p can never be smaller than h cross by 2. And this immediately tells us that the half h cross omega that we had obtained for the ground state is actually the minimum possible value. You cannot go below half h cross omega as far as this gap is concerned, at least not for a harmonic oscillator. But can you get this without using the ground state? Well, you can get this to be equal to half h cross omega if two things happen. If delta x delta p is equal to h cross by 2 omega, half h cross omega, exactly that. Delta x delta p is exactly half h cross. And if this term is 0. But that is exactly what a coherent state obeys. So for a coherent state, I've said apart from the ground state, but actually the ground state is also a coherent state corresponding to alpha equal to 0. So the coherent states satisfy the lower bound, half h plus omega. So you can have non-trivially oscillating systems, which will actually give you exactly the lowest possible gap between energy and the classical energy from the amplitude. Now, I will just quickly pass over the question of time evolution of a coherent state, which is also why they are very useful. I'm going to skip this simply for want of time, but it's a pretty straightforward calculation. You can all do it yourselves. In the end, what happens is, well, apart from a trivial phase factor, which has no physical meaning, alpha at time t, if you started with the eigenvalue alpha at time t equal to 0 for the lowering operator, the eigenvalue at time t simply becomes alpha e to the minus I omega t. Simply, it stays coherent, just the eigenvalue changes. Eigenvalue picks up a phase factor. And as a result, you can easily calculate things like how do things like x evolve. The expression of x at time 0, which is alpha plus alpha star. Apart from this factor, we have already used that before. And at time t simply becomes alpha e to the minus I omega t in place of alpha, and alpha star becomes alpha star e to the I omega t. And from this, you can again rederive the result that we had found. And you will see the basic idea that if you start with a coherent state, which is a minimum uncertainty state, it stays a coherent state as time progresses. All that happens is that the center, which is at alpha, keeps on oscillating. Now, we come to a rather more mathematical part here, but which is important for the introduction of squeeze states. So let's quickly take a look at this. We have actually seen that up to a normalization, up to an exponential minus alpha mod square by 2 factor, a coherent state of the harmonic oscillator can be written down in this form. It's a superposition of the number eigenstates with eigenvalues alpha to the n by root n factorial. But remember, the ket n is basically something you can get out of ket 0 by applying a dagger n times with a normalization factor square root of n factorial. Now, this square root of n factorial is rather nice because it combines with this square root of n factorial and gives you this. So what we have is this operator, which is an infinite sum of alpha a dagger raised to the n by n factorial acting on ket 0. But I'm pretty sure all the students here have recognized what this sum is. X to the n by n factorial, when you sum it over all n from 0 to infinity, is exactly what you call the exponential function, e to the power. So, apart from the normalization, you get the ket alpha is nothing but exponential of alpha a dagger acting on ket 0. Rather simple form compared to this infinite sum and so on. But there's one thing which is slightly not too good here. The normalization has gone wrong. Exponential alpha a dagger up to ket 0 will just give you this sum, not the normalization factor. It's also easy to see why that is. When a state gets acted upon by a unitary operator, its norm doesn't change. Exponential alpha a dagger is not a unitary operator. But you can easily get a unitary version. Not this, but again, this is a result which should be familiar. If you take the exponential of an anti-Hermitian operator, then the exponential is unitary. So all you have to do here is, instead of alpha a dagger, change that to an anti-Hermitian operator by subtracting from it its Hermitian adjoint. So if you use this operator, which is unitary by construction, and apply this on the ket 0, you actually are going to get a normalized ket. But this is a different operator from this one. So are we sure that we are going to get the ket alpha back? The answer lies in something called the Baker-Campbell-Hausdorff formula, which essentially tells you that since operators do not commute, you cannot write e to the A plus B as e to the A times e to the B. This is a very familiar result, but let me just leave this as an exercise for the students also, that this thing breaks up into e to the A into e to the B times an extra factor, which is exponential minus alpha mod square by 2. This essentially comes from the fact that A and A dagger's commutator is 1, and all higher order commutators are actually 0. So D alpha acting on ket 0, is it really our ket alpha? It's a normalized state, no question about that, because it's a unitary operator acting on ket 0, which is already normalized. So this is what it is. This is the Baker-Campbell-Hausdorff result. We have broken up the exponential into 3 pieces. Now this one is just a pure number. So it can just be pulled out of the whole thing. You can put this in the front. That's just the linearity of these two operators. The exponential of minus alpha star A, which acts on ket 0, is, if you break it up, the exponential of any operator is identity minus that operator, actually plus that operator. The minus sign comes out simply because you have minus here, plus that operator squared by 2 factorial and so on. But notice that the ket 0 has a special property. It's a ground state, is killed by the lowering operator and all its powers. So all these additional terms will give you just 0. Only the identity will act on ket 0, and you will have ket 0 back. And now we are back to familiar grounds. Exponential alpha A dagger acting on ket 0, which we already know is this. And this is exactly our ket alpha. So the displacement operator, e to the power alpha A dagger minus alpha star A, does give you, when it acts on ket 0, the coherent state ket alpha. In fact, all the properties of ket alpha that we have derived and more properties can be just easily found out once you know this and you know how to handle exponentials of operators. So I will skip this part. This is just trivially showing that we can rewrite all the results that we had before. I will just skip this part for want of time. Again, calculations are pretty straightforward. But the reason why we had to bring in the displacement operator is to introduce you a second kind of unitary operator. It's called S of beta. You will realize why S very soon. It's very similar to the displacement operator, except that you have A dagger square and A square instead of A dagger and A. Now it's easy to see that this thing in the exponent, which is being exponentialized, is actually anti-Hermitian. So this is a unitary operator. And again, let me leave this as an exercise. You need to calculate S dagger AS and S dagger A dagger S for our results later. I will skip over this calculation again, lack of time, but you can actually, because I do want to keep some time for questions. Again, the calculation which should be pretty easy for all of you to carry out. Let me just give you a hint here. You just call this thing here y, and then you know that this is e to the y a hat e to the minus y. There is something called the Baker-Hausdorff lemma, which is very, very useful. My PhD thesis was almost entirely built out of that lemma long ago, nearly 30 years ago. But still, using that, all you need are repeated commutators. Now, why this operator is commutated with A is very easy to calculate. It's 2 beta A dagger. That with A dagger is 2 beta star A. Again, a very simple calculation. And that allows you to calculate all the repeated commutators. This is when I write YA2, and this is really Y's commutator with Y's commutator with Y's commutator, etc., 2n times with A. And these repeated commutators can be calculated, and this immediately tells you what these S dagger AS and S dagger A dagger S are. Let's leave this as an exercise. But the reason why that's useful is you can define now something called a squeezed vacuum state. Now you realize why we call this S. This is the so-called squeezing operator. And you start with this, the results that you just found out. You want to calculate this, beta A hat beta, bra beta, operator, loading operator, ket beta. Notice that the ket beta is S beta at 0. So its adjoint gives you the bra beta is bra 0, S dagger beta. And so this is nothing but the vacuum expectation value, bra 0, ket 0 sandwich of S dagger beta, AS beta, this operator. And since both A and A dagger have 0 expectation values in the ground state, this result follows. Similarly, this follows. But when you are talking of A squared, you have to take this operator, multiply it by itself, and find its vacuum expectation value. So when you multiply this by itself, you get A square operator, you get A dagger square operator, you get A dagger, you get A dagger A. Only A dagger has a non-zero expectation value in the ground state. It has an expectation value of 1. So you can easily calculate this. This is really much easier to calculate than it looks. Similarly, when you're calculating A dagger A, you have to multiply this operator by this operator, keeping the order fixed. And then take the vacuum expectation value. And the only one which will survive there is the A times A dagger bit, which will give you 1 from the A dagger's expectation value. You get sine hyperbolic square. And these two things multiplied together simply gives you 1. So this is your result. Similarly, all the expectation values can be calculated. I'm just showing you how it can be done. But if you do the calculation till the end and go back to our dimensionless x and p, for x, you get this. X, you get 0. For x squared, it's a slightly more complicated calculation, longer. Again, not really very difficult. You can simply get this by substituting the values. The difference between this and the square of this, which is of course 0, gives you delta x squared. And you can easily show that if beta is real, delta x simply works away half of it, so 2 beta. And a very, very similar calculation gives you delta p, the dimensionless momentum operator's variance is half e to the minus 2 beta. So the uncertainties again have a product which is 1/4, which is the minimum bound for these variables. However, you see, depending on the sign of beta, whether beta is positive or negative, either delta x or delta p will have lower uncertainty than half. Remember, some time back in this lecture, we had showed that a coherent state has delta capital X and delta capital P both equal to half. So the product was the minimum possible, and their uncertainties, individual uncertainties, were equal. Here, what you see is one of the two have a lower uncertainty at the expense of the other one. Of course, the product is 1. So if one has a lower uncertainty than half, the other one has to have a larger one. But what is important is one of them has an uncertainty which is lower than what is called the quantum bound. The quantum bound really is not a bound for an individual thing. The bound is only on the products. But for an individual delta x or delta p, you can get a lower uncertainty. And this actually allows us to do experiments that are way more precise than that is suggested by quantum uncertainty bounds. Now, I could have kept on going about these states and for almost forever. And there are other kinds of coherent states depending on what kind of system you're talking about. Then you can do path integrals using coherent states and so on. But let me just finish with how these connect to practical applications quickly. So in the quantum theory, the electromagnetic field can be shown to be equivalent to infinitely many harmonic oscillators of different frequencies. Now, this is a result which I'm stating. Once you study quantum field theory of the electromagnetic field, this is one of the first results that come out. And basically, this is where we get photons from. When you say an oscillator of frequency omega is in the nth excited state, that is the same thing as saying you have n photons of frequency omega. Basically, that's at least free field theory is in essence is just this. You have harmonic oscillators, whether it's photons or bosons or even fermions with a slight twist. You have harmonic or fermionic harmonic oscillators, where excited states of those harmonic oscillators essentially are particles. Now, one result, which I'm pretty sure all of you know, and this is where the name coherent for the coherent states comes from, is optical coherence. The fact that two light beams, how well can they interfere with each other? How well they are in step with each other? Lasers, as you definitely know, produce maximally coherent light. And the quantum state produced by laser light, perfect laser, would actually be a coherent state of the corresponding harmonic oscillator in this description. Which is why coherent states are actually called coherent states. They're connected to the most coherent possible state of light. Now, when you take a coherent state that is produced by laser and pass it through a nonlinear medium, now this is where I'm hand-waving a bit because there are many details to be talked about. You can actually get those harmonic oscillators, underlying harmonic oscillators, in squeeze states. And what that will do is that either the electric field or its quadrature phase field will have lower than minimum possible uncertainty. Now, this can be exploited for making precision measurements which are more precise than the quantum bound allows, like in the LIGO detectors. There you definitely need squeeze states in the interferometers, because when a gravitational wave comes and hits a LIGO detector, there are very small changes in the length of the arms of the interferometer that is being used. But those changes are too tiny to be observed if we are using ordinary states of light. You have to use squeeze states to be able to detect those changes. Now, I think I have sort of exhausted what I wanted to say. I have skipped over some things, but I'm pretty sure the audience can work them out if they want to. So I will now stop and ask if there are any questions.
Any member of the audience would like to ask any questions? Please raise your hand so I will unmute you. Anyone?
Oh, if there are no questions, let me just take one moment
Sure.
No, this is not about the talk at all.
Okay.
I just want to correct one thing in my introduction. My institute has no engineering connection, actually.
Oh, okay. That's
It's actually in the
education.
Institute of Science, Education and Research.
That's my mistake.
No, that's okay. I just wanted to dispel that.
Absolutely.
Any idea that the audience might have that we are an engineering institute. Not that engineering institutes are bad, but well,
You are not doing technology. You are not.
Well, Ministry of Education already has IITs. We are ISAs, which are the science equivalent of the IITs. So just to clarify.
Okay, thank you. Thank you very much.
Okay, can I just
stop sharing, please.
Stop sharing, yeah. How do I stop? There is no.
Okay, let me.
I can't see a stop share video.
I can do that.
I think you can do that.
Yeah. Okay, it's done now. So I would like to thank Professor Ananda Dasgupta of IISR for delivering a wonderful lecture. So now you have a question from Arnab Pal asking to know, Professor Dasgupta, you have a question now.
Yeah, please.
He says, explain coherent state. Please explain coherent state.
No, that was I thought that was what I was doing.
Yeah, I know. That is the question.
Exactly what kind of explanation do you want? That's the question. Well, a coherent state for a harmonic oscillator happens to be the eigenstate of the annihilation operator or lowering operator. A acting on a state gives you that state back with a coefficient. Now, why are we, so I'm essentially repeating what I said, but this is important. Why are we interested in coherent states? Basically, they give you the closest equivalent to classical behavior. They are minimum uncertainty states. They are states which show oscillations which are almost nearly classical in terms of expression of x and expression of p. Oscillations which have the same frequency omega as the oscillator, which of course every state of the harmonic oscillator has. But also the energy comes closest to the amplitude there. Also, they are extremely useful basically because they describe lasers, which are of course very important, useful things. Once you treat the light field using quantum field theory. And squeeze states are basically states which, in a sense, do one better on coherent states. They actually are also minimum uncertainty states. But in one of the two quadratures, the uncertainty is even lower at the expense of the other quadrature as well, of course. But once you have that, ultimately what you end up with is a state of light, if it's a squeeze state, can give you much more precise measurements than ordinary light can.
Yes, yeah, right.
Does that answer your question?
Are you okay? Are you satisfied?
Now, are you able to hear me?
Yes,
Yeah, I can
yes,
hear
you
you.
can be heard. Yes.
So now just I want to see what should be the, I understood, but what should be the clear cut? Actually, you have removed your slides. Just why I want to say the definition. What should be the definition in one or two sentences
Well,
of the coherent state? That I want to.
okay, that is a bit of a problem, basically, because depending on the kind of coherent state you're talking about, there are many possible different definitions. If you are looking at the harmonic oscillator, I can give you one immediate definition. The lowering of an eigenstate of the lowering operator is a coherent state. Now, it's also a displacement operator, d of alpha a dagger minus alpha sat a, acting on the ground state. Now, there are other situations like coherent states for spin, SU2, or coherent states for other systems, where the minimum uncertainty or the lowering operator eigenstate. For example, when you're talking of spin coherent states, you cannot have a lowering operator eigenstate. For the same reason why you can't have an eigenstate for the raising operator of a harmonic oscillator, because the spectrum is bounded below for the harmonic oscillator. For spin, the spectrum is bounded both above and below.
That is, I am interrupting. That is due to shortage of time. I am interrupting you. I understood that the lowering A has got the eigenstate, but A dagger does not have. But I am telling you, when two states will be called coherent states. When two different states will be just.
Look, I'm pretty sure that's the matter. You are confused. I think there's a confusion here. The confusion is between the light usage. So we did not really talk about that at all. When you say two differences, I mean, I think you mean two differentiates of light, right?
Yes.
Yeah.
Yes.
When will they be called coherent? The answer, again, is really not related to my lecture today, because all I used was, if you were to use two lasers, which would be very coherent, then you have a measure of coherence already, right? In optics, you have a measure of coherence. And in the quantum version of the theory, there is something called Glauber's measure of coherence, which uses the quantized fields to measure this. And according to that measure, also the maximum coherence occurs between, if the two lights are in maybe two different coherent states. That is, the two light states would have underlying harmonic oscillators. All light states can be described that way. And if one of the harmonic oscillators with a particular frequency omega, if both of them had the same frequencies, two lights, same frequencies, but the states underlying harmonic oscillator with that state would be in the coherent state. The coherent state that I described. Then you will have
And
mathematical
all the
coherence.
eigenstates of the lowering operator will be called the coherent states. All
Yeah,
the
that-
eigenstates.
That is the terminology. It's called a coherent
That
state.
is the term. That is the definition. You are
That's a
saying.
definition. Yeah.
If I may interrupt, I think
Okay.
we're running out of
Okay, I'm
time.
stopping here. I'm
Dr.
stopping
Pal.
here.
Yeah, thank you for asking the question.
I am actually Sudarshan Pal, former teacher of Kharagpur College.
Oh, it's written on
My
your Pal.
computer is not
So you have used somebody else's
functioning well. That's why today I'm using my son's computer.
Oh, I see. That's why I didn't get that. I got the name
Okay.
from there. But thank you for asking the question. And thank you, Professor Dashgupta, for a wonderful lecture and also for explaining the queries. Thank you very much. Because of shortage of time, I would ask Dr. Shinjini Dashgupta to propose a vote of thanks before we close this session. Shinjini?
Thank you, ma'am. But before that, basically, I got two messages, one from Dibyendu Sarkar and another from Surajit Chakraborty sir. So
Okay.
can we discuss it or?
Yes, sure. Why not? Absolutely.
Yeah. So can I just unmute them so that they can directly interact with?
I can. Yes, I
Okay.
can.
So I'm unmuting them. Yeah. Okay. Okay. So Professor Sarkar and Professor Chakraborty, both of you are now unmuted. You can directly interact with our resource
They
person.
have to unmute themselves, actually.
Yeah.
Hello, sir.
Yeah,
Please
Can
go
you hear
ahead.
me?
but Professor Chakraborty is
Hello, sir. Can you hear me?
Yeah, I can
we
hear
can
you.
hear you. We can hear you, but I'm trying to unmute Professor Chakraborty.
So I heard everything. Now I am a bit confused, like the quantum state and how you measure it.
So depends. That's a very complicated question and a long and very complicated answer. Not only that, it's almost always impossible to measure unless you have some prior knowledge. In fact, that's one of the major reasons why quantum cryptography is so useful, so successful. You can, well, your question actually is relevant here because something we did not really talk about. These coherent states, for example, are actually not orthogonal states. Two coherent states with two different values of alpha will not really be orthogonal to each other. Now, if states are orthogonal to each other, then they can be immediately distinguished from each other. Non-orthogonal states, there's a problem. So you can distinguish two coherent states which have very distinct or different alpha values. That is, if alpha minus alpha prime modulus is large, then they're almost orthogonal. You can distinguish between them. Otherwise, you can't. If they're very close to each other, then you cannot really distinguish them with reliability. But if you're using a laser, then you can actually control which coherent state you're producing by controlling the intensity of the laser and its frequency. And then, since you already know the states you're using, you can actually easily figure out what you're going to get out. So if you have known possibilities which you can distinguish between, then quantum measurements can actually work easily. I'm not sure whether I could answer your question because I'm not very sure whether I understood your question, whether you are talking of this or something else. Dibyendu, I think you can unmute. Do you unmute yourself or?
Yeah, now he can unmute himself. Yeah.
I think Dibyendu has been muted again. Or
Okay. I've asked her to unmute.
Yeah,
Yes, yeah. He can speak now. Yeah.
Yes, it's now. Yes, I have asked this question, and yeah, I'm
So
not
I'm
a
not
professor.
sure whether my answer was satisfactory, but
Yeah, I have to also read something.
okay.
It is just a little bit beyond from my prior knowledge.
Okay.
Okay, but you got a,
Shojita, you wanted to ask something?
Yes, am I audible?
Yes,
Yeah,
you
yeah.
are.
Yes, yes, yes.
are.
You are.
So,
You are.
so can I mean, it's a very small question. That is there any lower limit to delta X or delta P in the squeeze test? Because it can go below half.
In
How
principle, no.
low it can go?
In
Or is
principle,
there,
no. There is no lower limit in principle.
so
There
you
is
can
a
make
lower
delta
limit.
X 0 also, is it?
Well, you can get very close to 0. The product
Okay,
still
so
has to be.
very close. I mean, is there any limit to that very close or just very close?
Theoretically, there is no limit. You can go as close to 0 as you want. Technologically, of course, there's a limit, depending on the kind of states you can produce.
So it will be only technological limit.
Yeah, there's a technological bound. You can,
Okay.
but of course, squeezing us too much has other problems, because remember, while the coherent state stays coherent, a squeeze state does not stay squeezed that easily. It's actually evolves, and even if you manage to get a very, very low delta X at a particular time, it's not going to stay that low later on, perhaps.
Okay. Okay. Thank you very much.
Thank
Once
you.
again, thank you very much for a wonderful talk, Ananda.
Yeah, it was a wonderful.
I don't know, there were way too many equations, but still, and way too few pictures. I should have put in a few more pictures at least.
But it was very, very good. Thank you. Thank you, Professor Dasgupta. So Dr. Shinjini Dasgupta will now deliver the vote of thanks. Let her propose.
Thank you,
Shinjini?
ma'am.
Yeah.
Thank you, ma'am. Good evening, everyone. It is my pleasure to deliver the vote of thanks at the conclusion of the enriching lecture series organized by IAPT RC15 in order to celebrate 100 years of quantum physics. First and foremost, I extend our deepest gratitude to our respected resource persons, Professor Bhupendra Deb and Professor Ananda Dasgupta, for taking time out of their busy schedule to share such profound insights into the advanced theory and applications of quantum mechanics, like quantum computers, coherent and squeeze states, and their applications. Your lectures were not only thought-provoking, but deeply inspiring. Your expertise has given us a clearer vision of the future of quantum technologies and their vast potential. I would like to take a moment to express our heartfelt appreciation to Professor Monimala Dash, who played a vital role in making this event seamless, engaging, and well-paced. Thank you, ma'am, for steering the entire program. We also express our sincere appreciation to the organizers whose behind-the-scenes efforts ensured the smooth execution of the entire lecture series. To all the participants whose presence gives a life to the event, thank you for your enthusiastic and interactive involvement. As we conclude, let us carry forward the momentum we have built here and continue to explore, question, and innovate in the exciting realm of quantum technology. Thank you once again, and I wish you all a pleasant evening ahead. Thank you all.
Thank you. Thank you, Shinjini.
Okay, thank you. And
So the
it was
event
great talking to you. I'm not sure whether it was equally great listening to me, but still. Anyway, I will leave now. Your permission?
Yes. So now we can close the meeting. Yes.
Yeah.
Thank you, Ananda. That's really a very nice talk. Yeah.
Good night, everyone.
Good night, everyone.
Yeah, actually.